last session you learned basically how to draw a layout. What we are going to do now is to achieve the same result with scripting. Yeah. I have a small problem because I prepared a few scripts on GitHub. I don't know whether you can download them. Otherwise, we'll do without.
We can.
What happened?
If we could
download it.
Yeah,
I do have two GISTs that I would, if you can access them, but I don't know how to share the link. Honestly, it's the way to share a link with you.
maybe in the chat of the Teams meeting.
In the chat, okay. Then let's do that. Then. Okay, let's see whether this works. We'll see. Okay, so basically, a brief introduction. Why scripting? I mean, first of all, of course, you don't want to, let's say, when you have a big layout and you know how to generate it through formulas or code, you want to utilize this this option also to repeat the process. You don't want to draw things and change that over and over again. If you have an option to automate the process and to tweak it, adjust it, that's why we want to do scripting. There are some more applications for KLayout and scripting. Some people use it to extend the application. So instead of just generating layout, you can also create new menu features like functions which manipulate layout in certain ways, or simply do kind of other things like asking databases or whatever. People have done a lot in that respect. So it's not just confined to layout generation. If you know Cadence, you know Cadence also has a way to generate user interfaces. KLayout has the same features built in. Another application for scripting is if you want to code P-cells. P-cells are eventually cells which have parameters. So P-cells act as normal cells, but you can say this P-cell is, for example, the via we have generated before, but you can tell it to have a parameter telling you how many vias you want to have, 2, 3, or maybe an array of vias. Like you can configure this P-cell. You can basically think of a P-cell of the same thing we did before, of a normal cell, but technically it's something entirely different because it's not drawn. There's code generating this P-cell or this layout. I will not cover this today because it's a bigger topic, but if you like to know how to do it, there are tutorials about this and I can tell you about this as well. And also scripting is used in analysis of layout. Many people use it to, like, for example, compute the area of some features. This is sometimes important because a certain area density is important as a manufacturing parameter, things like that, or find a certain feature or things like that. And also verification, so design rule check and layout versus schematic is also implemented in terms of scripting. So these are the applications. I will basically focus on the first point today. If you'd like to know more, then of course I'm available for that. So this is hiding. What is this intended? The bottom line is hidden. Yeah. So is this all for me?
If you put in the mouse, yeah. Oh, no. Yeah, just keep the mouse in the middle.
Okay, it's yours, I guess. Anyway, okay, as I told you before that we have 2 scripting engines available in KLayout. In the SDF environment, we don't have Ruby, which is not painful here because we want to focus on Python.
Keep the mouse in the middle.
And Python comes in 2 flavors, so you can use the one internally built in, as you can start the application, the same thing we did before, and you can run Python scripts inside this application. So the application acts as Python interpreter, but you can also install the KLayout module from PyPy, which is the Python package repository, and there's one module which is called KLayout. You just install it, and you get part of the API. Specifically, the things I show you today are mostly available in this module. The only drawback is that the module name is different from the one I show you here. So wherever I mention the module name, which is PyYA in KLayout inside, you have to substitute it by KLayout DB specifically. I will tell you how to do this eventually. So you cannot run scripts exactly in the same way inside the application than outside. The background is that the PyYA module name was already taken in PyPy, so I couldn't change it. Otherwise, I would have done so. And a very nice way of using that module is type it into Jupyter Notebooks, but you can also use it in Pycharm. What I will do today, I will show you how to use it inside the application, but the knowledge you gain here, you can easily also apply to the Python module. Okay, I think we'll just start. Okay, then I'll show you how it's done inside the application. So if we have our application window here, there is one menu called macros, and there's a menu called macro development. And this opens this tiny IDE. This IDE is not, it's not competitive when you compare it to Pycharm, but it's quite nice. So you can do a lot with it already. You can, there's a debugger built in, and it has syntax highlighting and so on. So I think it's good enough for small experiments. If you like to develop bigger projects, maybe you would rather like to use Pycharm. Maybe people have managed to use KLayout as a Python interpreter inside Pycharm. Honestly, I never have done this myself, but apparently it's possible to configure Pycharm to use KLayout as a Python interpreter. So this means you can essentially use Pycharm, run a script, and it will launch KLayout and it will execute the script there. I think there are some links in. I think you should Google maybe. I don't know. Maybe I can find out this whether there's a description how to do it, or find out myself. Eventually, but when I'm talking about big projects, maybe I'm talking about things that have 20, 30 files. And if you go that far, maybe it's even easier to consider this Python module, to use this Python module. Okay, let's start. Let's close this. When you start this IDE, you should. You have something already? Okay, here you have an empty window, basically. So it looks like that. This is my window. Okay, I don't know. The others, maybe if you start macro and macro development, then you will see something on the SDF. In the SDF environment, you only see that tab. Python tab, yes. You don't see any other, because that's because Ruby is not installed, and that thing is for developing scripts to build kind of three-dimensional views. That's also not available on the SDF environment, maybe because there's no OpenGL. I don't know. Anyway, this is enough as of now. And so what you do first is you create a new script, which we will use as a kind of sketchpad to develop code. And you hit this, what you do is you hit this button here, the plus button, which will create a new script. And then it will ask you about what type of script you want to generate. And basically there are two types that are important here. So one is the general KLayout macro, and the other one is the third one, which is a Python script. So the background is KLayout does have a generic, has a format which is an XML format, which is generic. So it contains information, for example, which language you run, because KLayout has Ruby and Python, and maybe in the future Go or whatever, Rust, I don't know. And so the script contains a header, and this header tells KLayout whether to use Ruby or Python or any other language to execute. So if you choose the first kind, you give KLayout a little more information, so you can run the script, give it someone else, and these people don't even need to care what kind of language the script is written in. So that's why I would propose to use that here. On the other hand, when you build modules that you want to import into another script, they have to be Python, plain Python text, because Python cannot include these kind of LOM files. So that's why we have the second type. For you, currently it doesn't really matter as long as you know that Python files are Python files. But I will use the first kind. There are some additional benefits from using that kind. Is, for example, when you have created a script, you can easily show it in a menu, because you can say show this script in a particular place in the menu. And so you can easily configure the script to be displayed, and you don't need to worry. Yeah.
In this terminal, we have access to Qt, right? Like import Qt or something like that, because everything is made on Qt.
Yes. So we went, okay, this is probably not. No, what you mean here is probably the PyQt.
PyQt.
Yeah. Okay, that's a problem. So KLayout comes with its own PyQt.
Yes.
But it's not the same. So you cannot just import PyQt, but I can show you later how to do it.
No.
Yeah. The problem is
it's not important.
Yeah, no, that's a very valid point you're addressing here. The problem is the PyQt is not open. PyQt.
Right.
It's not open in the sense of license, but open in the sense that I can combine other systems with PyQt, because PyQt doesn't have a data structure which is accessible from the outside. So when I'm using Qt and KLayout, it's a different Qt than PyQt uses, and PyQt cannot access the Qt inside PyQt.
That's for PyQt. For instance, we have PySide. No.
PySide, okay.
But I think this is outside the.
It's outside, but I can tell you, KLayout comes with with a big part of the Qt API built into KLayout, into the Python library. So you can basically do exactly the same than you do with PyQt, pretty much the same, except that the module names are different.
So that means that KLayout implements part of the Qt API.
Yeah, basically we coded PyQt. But in a way, it's compatible with the Python extension that Qt implements. That sounds a bit weird, but I couldn't PyQt. Yeah,
it's another problem.
Yeah, the problem is if you have a PyQt object, I cannot look into this object because PyQt is opaque and not transparent, and that's why I cannot, let's say, bring together the application and PyQt. That's I would say that's a design flaw into PyQt, inside PyQt. Okay. Anyway, but the answer, I mean, if you like to generate UIs, you can essentially use the same code in PyQt, maybe with a few changes, minor ones, I'd say, and then you can essentially do the same here. Okay. Yeah, this is an advanced topic, but if you're interested in that, I can show you how to do it. I mean, I'm here since until Thursday, so there's enough time. Okay. Anyway, so this means I have created a new module or a new script, and I can change the name. So I change it to demo. Just type here, or you can also click here and then change the name if you like. The name eventually doesn't really matter, and you see the script is already populated with import PYA. That's PYA is the namespace of the module or the KLayout internals. If you use the standalone Python module, it's import KLayout, and then there are submodules. And the one we are using is DB mainly. So what you can do is something like that. If you're using the standalone Python module from PyPy, and then you can essentially use the code the same way we do here. But I'm not going to do this here because we don't have standalone. Sorry. Would you like to?
KLayout from us BYD.
Yes, but don't try to execute it here because it won't work.
Is there like a way to know which version you're in? Do F inside KLayout and import file else import KLayout?
Yeah, the problem is that what should I say? When you install KLayout on Windows, it comes with its own environment. Because in Windows there's usually no system Python. So and my own environment means I pull in all the shared objects, DLLs, and whatever comes with Python. And I didn't pull in the whole system, including pip and so on. And even if I did, I would need to give you some command line, which then accesses this environment. I know that people have asked a couple of times for using some system environment, which on Windows is not available, but I could use Conda, for example. So I already tried myself. I can basically build against Anaconda. But if I would deploy this way, then you would always have to install Anaconda plus KLayout, otherwise it wouldn't work. And it's a bit of trade-off. So people like self-contained applications, and that's why KLayout comes with its own kind of partial Python thing. I mean, my recommendation is always if you use Linux, then you can essentially import or pip install every other module, every other package you want to have, like NumPy, SciPy, whatever. And then you can easily use it inside KLayout because it shares the system Python. So it's unfortunately a bit, it's even more messy on Mac, because on Mac there's Homebrew, there's Anaconda, there's I don't know how many. There's a system Python, so people never know what program accesses what, and it's a kind of mess. And I would prefer having that in Anaconda, and I would even prefer more to have KLayout as a package in Anaconda, but I didn't manage to convince them yet to include it. Okay, anyway, so this is where we are, and let's just do a simple thing. So let's just print the usual thing. But okay, this keyboard. I have not been using this keyboard for a while because I was always using the external keyboards, and now this got kind of sluggish. Okay, now when you have finished your script, you press one of these buttons. If I press this button, first it will ask me to save it, which is a good idea. And then you see this icon here, and this says this script is the current one. So if I press, I can have multiple tabs here, so multiple like that one. Now I have a second one open. And now if I press this button with the exclamation mark, it will make the current script, or the open script, the current one, and run this one, while the other button will run the current script, which is that one. Okay, that's a bit confusing, but sometimes you want to edit a script that is called by the other script, and you don't want this script to be executed, but the main one. So just keep this in mind. If you press the one with the exclamation mark, it will switch the current script to the open tab, and the other one will re-execute what you had before. And if I run it, then below you have the console window, and this shows you the output of the script. In addition, I can go there and enter commands there. So, and if I press OK, then it will execute this Python this Python command below. And which is very convenient because I can set breakpoints. So let's do something else. So now let's define a variable containing the message to be printed, and now click here. And if I click here, I create a breakpoint. And if I re-execute, okay, still asking to say, then it's the execution stops here. And now I'm in that context, so I can, when I'm entering a command here, I have access to the local variables, and I can also change them. Okay. And if I continue execution, which is done by just pressing this button again, then you see it displays the changed message. So the console also is interacting with the debugger. When you are in a breakpoint, you are in the scope of the certain of the current breakpoint. And that is pretty convenient if you want to investigate what your program is doing. I mean, don't expect too much from the system. It's not Pycharm, as I said, but it has. I think it's a nice entry-level IDE. I would say.
You coded this market development.
Yeah.
I mean, it's good.
Yeah, but I stopped trying to do everything that Pycharm offers. I mean, you have to imagine the whole thing is like 10 years old, and there was no Pycharm by this time. So there was no JetBrains and no. So well, and if you know the skill IDE that Cadence sells, I'd say this is much better. And I mean, I honestly, by supporting two languages, yeah, don't ask me why I support both Ruby and Python, but I mean, essentially Ruby was my first choice. Python wasn't on a level by that time I could really use it. And people asked for Python, so now I'm supporting both. And this is kind of special. So no, if you have Pycharm, for example, you only have Python, right? So and here you can like here when I switch to Ruby, it's somewhat different. The syntax is somewhat different, but similar. And this is executed inside the Ruby interpreter. So this is something you cannot do with Pycharm, so that's why. And this was a necessity here by supporting both. But it's like it was much too much work for the. I wouldn't do it today the same way. It's most tools I use or I see only support Python, and that's good enough. But personally, I like Ruby better than Python, but not many people share my opinion. But at least it's like 3 times faster. And Ruby is the language of choice for web applications, or for many, like because Ruby on Rails, that's a very frequently used framework, and that's favoring Ruby. But this is not a web application, so and honestly, Python it got extended quite a lot in the recent years. So by many very good modules like this, artificial intelligence, SciPy, NumPy, whatever. So these are really very good. And so Ruby is kind of specialized in web application development. Anyway, okay. So this is the first script. Let's see what's on my slides. So okay, so this is the basic window layout. Okay, we're already. Okay, I think before we really can start with scripting, I need to explain a little bit the theory or some theory about what is happening here. I mean, the most important thing, I guess, is about coordinate spaces that we have here. So we are talking about two-dimensional layout. We are not talking about three-dimensional. We are always using XY coordinates. And there are actually 4 classes that KLayout uses for coordinates. So there are 2 classes which are points and vectors. Both are X and Y coordinates. Okay? But points are global coordinates, so they are a specific point on the plane. And vectors are differences between points. We will see later why there are 2 classes. So eventually, when you have a point and you add a vector, you get a new point. When you compute the difference between 2 points, you get a vector. You can add vectors, but you cannot add points, basically. So I think that's a concept that's also used in math in general, at least in physics it is. So a vector is eventually a shift and a point is a location. It makes a slight difference, specifically, for example, if you apply transformations, we will see later. Plus, there are also 2 flavors of each of these classes, and one comes in integer units and one comes in floating point units. The background of this is that GDS as a concept and also open access and also other formats don't store coordinates as floating point units, but they store coordinates as integer units, integer multiples of some basic grid. And the basic grid is called the database unit of the GDS file. And typically, the database unit is some very small number. So before we were using, for example, 1 micrometer grid to draw on. The database unit is the most basic grid where I cannot go below. So the basic unit of coordinate. And in order to have some freedom, one uses 1 nanometer, for example, because we believe that we don't need coordinates which are fractions of nanometers. Today's technologies are, let's say, if we go down to 5 or 7 nanometer, then it seems like choosing 1 nanometer as the basic unit is a bit coarse. So that's why people tend to go to half a nanometer or quarter of a nanometer today. But basically, we are talking about a very small number. And these integer unit coordinates that we have inside KLayout, they are, for example, if you say 1,000, 2,000, it means 1 micrometer, 2 micrometer. If you have a database unit of 1 nanometer, because 1,000 nanometers is 1 micrometer. So, and because this always needs, you always need to know how many, or what is your database unit, and that's why we have floating point coordinates as well, and they are always read as coordinates in micrometer units. So coordinate, a floating point coordinate of 0.5 is 500 nanometers, in fact, if you have a 1 nanometer database unit. Is this kind of comprehensible? Okay, that's, I mean, the whole thing is, yeah, you simply have to use it. But when we are scripting now, I'm trying to consistently use these floating point units. It's a bit confusing. KLayout offers both versions, and it offers also both versions for the shapes we are using. So when we have a box, it comes in 2 flavors, one with integer units and one with floating point units. I prefer personally to work with these floating point unit objects because they are typically what you are using to describe an object. If you have a, let's say, the wire we have generated before, I want to use 1 micrometer as the width and not 1,000, because I don't know whether 1,000 is 1 micrometer or 500 nanometer, depending on the database unit. When I want to implement some physical layout, I prefer using micrometer coordinates, and that's why I personally prefer these floating point types. And problem is only you need to consistently use them. So you cannot, if you mix them, then you're getting rounding and things, unexpected results. We will see. I will show you. Okay, this is the explanation of the database unit concept. There's one important thing to know. In GDS files, the coordinates are coded as 32-bit integers, which means that you have a limited range. So, for example, if you have a 1 nanometer database unit, the maximum dimension of objects you can represent is roughly 2 by 2 meters or 4 by 4 meters. Of course, that's after the larger dimensions you exceed the 32-bit coordinate space, which is usually not a problem, right? So, I mean, we don't have chips like 2 by 2 meters or 4 by 4. But when people reduce the database unit to some very small number, like 100 of a nanometer, then they run into problems with these coordinate space limitations here. So because then we are not talking about 2 by 2 meters, but we're talking about 20 by 20 millimeters, and then we are already in dimensions which are below the typical dimensions of masks or even chips. And that's why basically KLayout also supports 64-bit coordinates, but you need to compile it in a special way. And some people do because they use picometers as database units. But if you imagine that a single atom is like 1/10 of a nanometer, physically it doesn't make sense to go below 1/10 of a nanometer. I don't know what they are doing actually, whether they work with subatomic particles or but technically this is something to consider. And yeah, I think you won't hit this boundary, but just in case you plan to draw your
technology node or it's user defined number as well?
The database unit?
Yeah, database unit.
Yeah, it's, I mean, today I think they switch, like I said, to a maybe quarter of a nanometer.
Okay.
It's typically defined per technology node. But when you're talking about drawing layouts, still even the advanced nodes still use 1 nanometer as far as I know, because it's simply, even if you have a 7 nanometer gate, you can still draw that nicely in a 1 nanometer grid or database unit.
Yes, I can relax my database unit if my technology node is high.
Yeah, I personally wouldn't do so unless you want to exceed this coordinate space. You want to, or your overall chip dimensions are more than meters. Then you have to relax the database unit. But usually 1 nanometer is a good choice.
For 180 nanometer, I don't have to go for 1 nanometer.
No.
So then I can go for 100 nanometer.
No, you don't. You just stay with 1 nanometer. That's for 180. That's good enough. Yeah. I mean, then your gate is like 180 pixels wide or units wide. That's still okay. If you want to have a grid by drawing, then you use the grid settings I've shown you.
Yeah.
You don't need to change the database unit. Okay. It's just a internal attribute or internal parameter.
Grid setting and this database unit goes hand in hand.
Yeah, I mean, not really. Okay, a grid has to be a multiple of the database unit.
Okay.
If you want to have a grid of let's say 5.5 nanometer, and you have a 1 nanometer database unit, that won't work. Well, I mean, small database units come into play when you do mask corrections later on, shortly before manufacturing, because they slightly shift the mask edges to compensate for proximity effects, and there you actually need a higher accuracy. Then they go down to 10th of a nanometer maybe. So this is when they make use of smaller database units. I mean, that's not quite important to know. It's just important to know that there is this parameter. We will see it in some places inside when scripting, and it's also important to know that we have 32-bit coordinates in GDS. And also the last points. Sometimes when you change layout in GDS, snapping happens. For example, if you convert a path to a polygon, then the points of the polygon, so the points of the path I've shown you were the center line. So they are on multiples of database units. And I convert this to a polygon, the outer hull, the outer contour of the path is written into a polygon, and then the contour points become polygon points. And this is when snapping can happen. For example, when I've shown you this 45-degree path, these corner points are technically not exactly on a grid, because there I have the intersection between a 45-degree edge and a horizontal edge. And technically that might not be on grid. So the polygon you generate is slightly off the original contour of the path. And this offness, or this difference, comes from snapping to the database unit. Okay, that's already quite detailed, so I don't think we need to go that far. And that I wanted to show you. This is kind of summarizing the what I talked about before, so the points and the vectors. So these are the 4 classes. And whenever there's a B suffix to a class name, this means it's a floating point version. Yeah? So I'm trying to consistently use D versions of objects. So there's for every, well, for most of the classes, there is a non-D and a D version. Like rectangle is a box, and there's a D box. And I'm trying to use D types, and because that means I'm using floating point coordinates, which are micrometers. Okay. Yeah.
So, for example, in that point, the first
Yes.
row, point 100 to 100, when you say it's a database unit, I think that's like
Yeah.
100 nanometer, 200, if the
database unit is 1 nanometer.
Yes. And then the one, the data point that's floating, it's all in relative to micrometer.
Yes, this is here. This would be micrometer, and this would be database unit.
Okay.
And I'm using the D point here to indicate it's micrometers.
Yeah, I mean, that's easier.
Yeah, first of all, I mean, these objects are quite simple. So these are two numbers simply. So there can be anything like kilometers or whatever, right? But it's a convention inside KLayout. If you use these points, for example, to generate a polygon or path from, then you mean this is micrometers. And KLayout knows that it has to, when it writes these objects to GDS, it has to compute the actual dimension by dividing by the database unit. Okay. Okay.
I have a question. How we manage the floating point error stuff? Like we give the example of 0.1 plus 0.2 is not 0.3.
Okay, you mean the rounding effects and so on. Yeah. Okay. KLayout internally always applies some fuzziness. Yeah. So, for example, if you compare 2 points, if you ask whether 2 points are identical, and you have 2 floating points.
We define an interval.
You don't necessarily have to care about this. KLayout does it for you, but it uses an interval which is, I think, millions of a micrometer. So it will apply always 1e minus 6 as a fuzziness internally. So you don't need to be worried about rounding effects, which later on give you weird results when you compare things, compare 2 floating point values. That's the problem with rounding effects when you use floating point. If you take, let's say, 0.1 multiplied by 10, then the result is not exactly 1, but it might be off. But that is one, I think that's the problem you are.
Yeah, the problem is that if we are, these errors accumulate at the end.
Yeah.
Maybe,
Okay, so if you're starting to do numerics here, if you're starting to do numerics, I would recommend not using these objects or to apply the same rules that you would when you do numerical computations. Like not, for example, if you iterate, if you want to generate interval values like 1, 2, 3, 4, 5. You can do so by using a value and adding 1 all the time. But this means you will accumulate rounding errors. Right? I mean, not for 1, but if you have 0.1, 0.2, 0.3, and you do this 1,000 times, then you will accumulate rounding errors over 1,000 periods. Right? But if you compute the value by using an integer times 0.1, you don't do so. And that's exactly, these are very simple techniques to avoid these problems. Right? And basically, you have to apply the same techniques if you work with the floating point objects.
Right.
So they're not safe against these kind of effects.
So one have to have in mind that this effect exists and it's integer when it is needed. Right?
When it's needed, you have to be careful about the same effects than you would have for a normal account. So,
thanks.
I mean, you're basically right. So using integer objects frees you from that concern. But on the other hand, you always have to let's say, keep in mind that you have a database. So when you're working with physical dimensions, you always have to compute the integer unit dimension from the physical one by dividing the database unit. I hope that's not too confusing. Oh, okay. I mean, that was a little bit of theory. Let's do something real. Okay. So the first thing is when we do something here, I think it's a good idea to give you something where you can script something and view it graphically. And that's why I have prepared something. I think it's better to share with you this gist. Because let's try. So I will put this into the chat. Oh my God. So can I access the chat when I'm presenting?
If you're presenting, just go with your mouse, I think, up, and it will fall.
Will I do?
Let me just put something in it, so maybe chat will appear. Do you see anywhere anything?
This one. So,
this one, okay. Okay, thanks. I know. So we found. So I shared with you a gist. If you access that. You should see a text which is that one. And what I would ask you is to create a new script, call it canvas, and copy paste this text from this gist into the script. So you have it.
Not in.
Oh, okay.
Oh, yeah.
So we'll do
Oh. Oh.
okay. So,
Send it again. I get ready too late.
okay, then I'll send it again. Did you get it?
Yeah. Well, no.
Okay, so don't worry if you don't understand this. No, it's actually quite simple, but it will define a function that allows us to easily see what we are coding. I will show you quickly soon what this is about. Does anyone else need assistance here?
No, I cannot. That's why I think there's no open, so that's just.
Yes. So you can send it again. No worries.
Thank you.
You can do so over and over again if you like.
Thanks for the Discord. Oh, thank you.
Okay. What?
Oh, super. I changed.
This is.
Oh no.
Oh no.
I move it.
It's on the recording. Does anyone need support? Okay. Okay, so
Little level.
when you have opened it, then please just run the script. So make sure it's run. And then we will do our first experiment here. What we will do. Okay. So we will create a box. And this is basically what we are going to do. So I'll try to leave this window here and try to do that myself so you can see how. So I take the console, I generate an object, and I type in these coordinates. So this is going to be a rectangle. Comma button is sticking. Comma key. Okay, I switched to Ruby. So make sure you have enabled Python here. Can you see this? And if I want to catch a previous command, I'd use the arrow keys. So up, down will bring me back the previous command. So, and if I execute this, I have, oh, this is really, the flip effect's more annoying. This is this command here, I have just executed, and this generates a box object, so a rectangle. And in order to see it, I'm using the script we have just written or just imported, and I will use this command. This command will clear my canvas, and this command will insert an object. And canvas means I will see a new layout. So let's just execute this. I don't need to clear it because I didn't have anything there so far. Why did I? Okay. Let's just close the layout, please, that you have there. So close the layout, and first of all, we need to generate a new one. I forgot this. So go to File, New Layout, and create one with at least a layer 1. So edit new layout, generate one with one layer, which is called 1. So I have 3 here, but this is what you should do. And this is what then is going to be called the canvas. So this small script I have provided will put my object onto this canvas, so we can see it. This is just for visualization.
We should name it canvas?
No, just name it whatever. Doesn't need to have a special name. So, any problems? So, and now, sorry for this. Now I have issued this canvas.insert, and it will put this box here so I can see it. It's just for you to take a look at what you have just generated. Okay. Because so far we have just created a single rectangle. Can anyone? Can you reproduce that?
Yes.
That's wrong.
How big? Okay, I need to specify the point, right?
Okay, so it's not working.
Isn't it the point?
So dbox, dbox. Oh, sorry, I need to let's bring it to the front.
We can.
Let's share this one. Here, this amount we need to. As you can essentially insert any kind of coordinates here. So
Make what bigger?
what it means is this dbox will create a box.
Yeah.
It's first of all just a rectangle without using this canvas thing. It's not shown. It's just a box object, and the coordinates are left, bottom, right, top. So you can use any kind of coordinates. I was using the a centered one, but we can use a different one. You see them, okay? So let's just take any other coordinates. So like using 0, 0, left, bottom, right, top.
Oh,
So I create a second one, and I use this canvas insert. And now I should see 2 boxes. Okay. I'm sorry if that is. I can. Is this easier to read for you this way? Okay. Okay, this we don't need, but. Let's make things bigger. So is this easier for you to read? Even larger than this?
Yeah, I got
Okay, you got an error. Saying what? Sorry.
I tried.
Just check it. Don't know. No problem. Okay, and are you successful with that? Any problems? Okay, so now that was only preparation. So now we can do things. We can work with these boxes, and we can use this canvas just to display it. These guys who do the GDS factory GDS factory project, they are trying to integrate this functionality into Jupyter notebooks, so you can issue commands, and then you have a Jupyter inside the Jupyter notebook, a display that just shows the objects graphically. Right now, I don't have something like this available, so I need to give you this canvas workaround. But I think once you have set it up, it's a nice tool to play with. It's a bit of a workaround. It's more. I mean, well, if you just want to print this box, I use strb, which is Python for turn it into a string. And then you see the box written in terms of Polygons. Okay. So this is also a way of showing the object you have just created. I wanted to show you because Python API or API in general, the knowledge how to use it comes of course from the documentation. I would like to show you where the documentation is, so you can start using it yourself. There's one thing, so there are two options. First is you press this button here, which is supposed to be a kind of light bulb. It runs a little because on the first call it will collect some index for the on-written help. Okay, should be done soon. So, and here it opens the built-in documentation. And when I want to know about the dbox object that I'm just using, I type in here. This is actually the documentation of the API documentation, so the formal documentation. And the second one is a documentation where I try to describe the objects more in a, let's say, hopefully comprehensible way. This is more or less what I'm explaining here currently. If you want to have the truth or the real details about everything, then you go to the API documentation, and this is how it looks like. And if you want to understand it, the knowledge about the coordinate order you have to give it is here in the constructor description. Constructor means the method or the function that will generate an object. And I was using the third version here. So this is called new because new is the Ruby slang for constructors. And here it is written that, okay, I need to enlarge this window, I guess. Here you see the order of the arguments. You also see that I have another option. So either I use no argument at all, and this will generate an empty box. So boxes can be empty, which means they have no left, right, top, or bottom coordinate. They have 0 points, and empty boxes are quite useful if, for example, you compute the intersection of two boxes, and they don't intersect at all. The result will be empty. Yeah. So a box can be empty, and a box can be specified in terms of 4 coordinates, and a box can be specified also in terms of 2 points. So the lower left and the upper right point. You don't necessarily to provide lower left and upper right. You can basically also take upper left and lower right, or even change the order. So KLayout will sort the points in a way that a valid box is made. And so in that sense, left is not necessarily left, it can also be right. And the box has a couple of methods and a couple of features, and we can start playing with that. So, like, let's create a second box. So, like, Let's not make it that big. Come on. Okay, now I have created two boxes. I have this one, and I have that one. Okay, and now let's show them. Let's take a look at them. So these are the two boxes I just created. And one of them is the tall one. So starting with 0, 0, going to 2 on the left side and 5 on the top. And then I have created a smaller one, 1, 2, 3, 4. And this is this box here. And I have put both on the canvas, so I can both see them at once. Okay. So, and now let's do something like compute the intersection of the boxes. So this is done. So like call it BI.
Hello. We are just looking for infrastructure in the room.
Okay.
No problem.
So this is how I compute the intersection between boxes. This is an operator. So Python, I have provided a couple of operators to work with. And now let's take a look how this looks like. Let's also put this, I don't know, let's use canvas clear. First get rid of the previous ones. And then we put this intersection box. And this is the intersection of both. You remember the one was a tall one, the other one was a small one. So, and there are a couple of these methods, not only intersection. But when you look into this documentation, there are a couple of operators. These methods I would like to skip, so they are underscored, they are internal basically. But you can, for example, compute the area of a box. So if I do so, like taking the area of this box, it's like 10 square micrometer. A box has a bounding box, which is the box itself. You can ask for bottom coordinate, you can also set it. So bottom equals means I will change the coordinate of the bottom. So like saying E bottom is 1, changes the coordinate. You see, this has changed, this value. So it has a number of features. So you can ask whether a certain point is contained inside the box, whether it's empty or not. You can enlarge it, so you can shift the sides of the box by a certain amount. It has a height. You can ask it whether it's a degenerated box without a width or height, so whether it's a single point. Left coordinate, you can move the box. You can check whether it overlaps another box. You can ask for the lower left or the upper right coordinate. You can compute the parameter. This will convert it to the integer type. If you give it a specific database unit, you can turn it into a database unit 1. You can ask whether it touches a different box. This transformed we will deal with later. Okay, so basically, a box is an object. A box has a couple of methods. It has a couple of operators. And this is the basis of a lot of shapes inside KLayout. So would you like to have a question?
Yeah, how can we put layer?
Okay. First of all, it's just a box what we created now. Yeah. What this insert, canvas insert does, it actually also already creates layer. Let me come to this later. I first would like to talk about the geometrical primitives. And the geometrical primitives don't have layers. They are just the boxes, right. And we will then build layout from that. Yeah. This is how it's done in KLayout. In skill, it's different. In skill, you say db create rect, and you give it a layer. So you don't have a standalone box as an object in skill. KLayout has geometrical primitives as objects, and these methods you have here, like the intersection and like bounding box and so on, and we'll come to much higher level operations for the polygon. So they are not available in skill because skill does not have a box object. Yeah. Well, it does, I'm not sure. At least I don't know. I don't know. But the function is called db create rectangle, and it takes a layer. Maybe skill has some features to compute, for example, box intersections. So. But the Pythonic or the object-oriented way of doing that is to define a class that represents a rectangle, and then doing something with this class. So you can modify it, you can work with it. Okay. Any questions regarding that piece? So then let's continue. So this is the box. Okay, as I mentioned, boxes can be empty. This is quite a useful concept. It might be a bit strange, but it's very useful for having a consistent model to work with. Okay, these methods I have shown you. So if you browse the documentation, you will find some more methods that might be useful for you. So whenever you miss something, just try to read the documentation, whether you have something there that might help you further. Then let's go to the next object. Edges, yeah, I just covered it briefly. Edges are not real GDS objects. So in GDS, there's no edge. But an edge is a very useful object. It's basically just the connection between 2 points. Right? And if you imagine a box, for example, has 4 edges. On the left side, top side, right side, bottom side. And edges play a very important role when it comes to computational geometry. When you, for example, want to compute the area of an object, of a polygon, you always traverse the edges. And then there's a formula how to compute the area. So the basis of such a computation are always edges. And also for operations like computing the difference or the intersection of 2 polygons, they also work with edges internally. So an edge is an object that is quite useful for implementing algorithms, for polygons specifically. Edges don't play a role for VLSI layout, because they are just lines. They are not something tangible, something physically manufacturable. So still, as they are useful, there are 2 classes in KLayout representing edges. So edge for integer units and d-edge for floating point units. And in order to create an edge, you need 2 points, obviously. And that's why the constructor of an edge has 2 points simply. And what is worth mentioning, which is hidden below here. Yeah. So when KLayout normalizes polygons always in a way that the contours of the polygon is counterclockwise. So clockwise. Yeah, clockwise. Okay, so they run in that direction. And if you imagine an edge running in that direction around the polygon, that means that on the right side of the edge, there's the inside of the polygon, and on the left side is the outside. So an edge is always a line separating some inside and outside. Yeah? And the convention is that on the right side of an edge, there's inside. And on the left side, there's outside. So this is consistently used within KLayout. So whenever you obtain edges from polygons, you can always be sure that the inside side is on the right side of the edge. It's very important if you implement algorithms like for computing intersections and things like that, or checking whether a point is inside. Usually you don't need to implement these algorithms yourself because they are already built in as methods. But it's a very useful convention, and it's enforced when you generate objects. This convention is always enforced. Okay, so let's talk about polygons. I've already touched it. Polygons are basically polygons, so a number of points that are connected. And KLayout has two kinds of polygons. One is a simple polygon. It only has an outer contour, so you just walk around an area, and then you have some inside and some outside. Basically, you can generate polygons which are self-intersecting. So they go around, they cut itself, they go back outside, go back, whatever. When you do so, I would say, well, it's a valid thing to do. But actually, what happens when you cross a polygon itself, when you go back and cross its own area, then you have basically a piece of polygon which is covered twice. And this means there's a certain, let's say, it's an open question what to do here. If you look at tools like Inkscape, like drawing tools, they sometimes treat such areas as being open. So when you have a polygon overlaying itself twice, sometimes this area is cleared. And that is called the even-odd rule, because when you think about a point and you think how many times this point is covered by the polygon, and sometimes people regard a point that is covered once, 3 times, 5 times as being covered, and 2 times, 4 times, 6 times as being not covered. In GDS in general, the convention is not even odd, but the convention is non-zero. That means if you cover a point 2 times, 3 times, 4 times, it's always full. It's always regarded full one. And since full for us means material, and full specifically means there's something conductive, it's very important to follow a single convention, because otherwise you might see something different on your screen than you finally have on your chip. And no metal means no connection. So you really have to be careful, let's say, not to establish a true convention. Unfortunately, GDS by itself does not enforce a certain convention. And I mean, I have seen chips failing because of that. So bottom line, the message is better try to avoid this. So if you draw a polygon, try not to overlap the polygon itself. So if you create a ring, for example, you can do so. And if you let the ends of the ring overlap itself, just let them touch and not overlap them. It's also valid for drawing. I think today the convention is almost everywhere to, in case of such overlaps, to still make a connection and not treat this area as empty. But I know tools that have switches that allow you to configure the interpretation of that areas. And if your mask maker uses a different switch than you were using in your viewer, then you will see layout which in reality is different. And that is really painful. And most foundries, if you send a chip layout to a big manufacturer, they often implement checks which make sure that you don't have such situations in your layout. So they forbid self-overlapping polygons specifically. Okay, and KLayout has a second kind of polygon, which is not a simple but a normal polygon. And the difference is only that normal polygons also can have holes. So imagine you can create a torus, which is a circle and a hole, or a donut shape, so a circle and a hole. GDS doesn't have polygons with holes. So you can do so, you can generate these objects inside KLayout. If you write them to GDS, KLayout will produce a cut line, so it will go around the polygon, then go into the hole, so making a small connection line, go around the hole, go back outside, and go back on the outer contour of the polygon. That imposes some manipulation of the original polygon, so which is usually safe to do. But the message is simply, if you generate such polygons with holes, you need to be sure that what you see maybe later in your GDS, so when you load it again, you save it, you load it, you will see something different. You will not see a polygon with a hole, but one that is inside, around the hole, outside. Okay. As I mentioned, contours, so the contours, the point lists are normalized to clockwise connection, but counterclockwise for holes. So this enforces this rule I just mentioned, so that edges have the inside of polygons is on the right side of an edge. And again, I have both objects in floating point and integer flavors. And yeah, so the last sentence says what I already explained. So polygons are basically can be seen as a number of points being connected, but they can also be seen as a number of edges making up the polygon contours. That's a dual view of the polygon, which is useful for some algorithms. That's why we have edge objects. So, and then we can try to create a polygon. And so what we do in order to create a polygon, first you need a set of points. Yeah? And I will do so by let's create a rectangle or a triangle. So I am generating an array. This is really annoying. So what did I do here? Okay, let's just. So P is an array of points now. So this is Python for array, square brackets, and up 1, 2, 3. Okay. So the first point is on an origin, the second one is x1 and 2 and y2. And the third one is on x2 and y0. So that's going to give us a triangle. These are only the points. And now I'm creating a polygon from that. And that is very simple. So that gives us a polygon. When I move this, this is how it looks in terms of string. So 3 points basically. And I can use my canvas to display it. So let's first clear it. So let's see what it did. Here, there's my rectangle. So this is a simple form of polygon. Yeah. So I could also have used the simple polygon, because here I'm not using holes. So this works as well. So if I generate a simple polygon, it basically looks the same. So there's nothing special here. So, but I can. There are many more ways to generate polygons. So having this point list is, of course, well, it's nice. Often when you want to generate, for example, a polygon which is just representing a rectangle, you could use the box object, but you can also use a box object to generate a polygon from. So I do have this B. B is still my box objects from the previous experiments. So this is the box I have, and I can use it to generate a polygon from that. So either a polygon or a simple polygon. I just creating a polygon object from that. So this is how it looks then, 4 points. And then let's again use the canvas. So, and now this is a polygon. Yeah? And you can tell that it is a polygon because first it says so below here. Here this shows me what I have selected. Okay. Okay, here, very small to see. It says it's a polygon with 4 points. And also when you look closely, the selection marker here shows only 2 points for a box, which is this and this point. Here it shows 4. And of course, if I double click, it will tell me that it's a polygon. And these points here. And there's also another nice thing. If I have a box, I can also generate an ellipse from that. It's a very convenient way to generate circles and ellipses. So what it will do, it will take the box and then fit an ellipse into it. And the 32 means the number of points, because it's not going to be a precise ellipse, but it will have 32 points approximating this ellipse. So this is, yeah, if you need it. I mean, the problem is that VLSI layouts usually don't use ellipses or circles, but it's a nice thing to do. And so what I would also like to do is I can show you how to generate boxes and holes. So, and let's do something interesting. I do have this B. B is a box. Huh? So what I can do is I can compute the center point of this box. So let's do a little bit of applied scripting now. So B is the box, the one that defined my ellipse. C is now the center of the box. C is a point. Center is a method that the box objects have. And then let's define a dimension. Let's use a vector. Let's use something like okay, so D is 1 dimension, it's a vector 200 nanometer. So X and Y displacement. And now let me define a new box, call it BH. And give it 2 points and use this E vector plus the center. So now I did this. Okay, C is the center of my ellipse. D is a displacement vector, so 200 nanometer up and down. Now I compute 2 points from that. Remember that the vector is something that I can add or subtract from points because it's a shift. And this will give me 1 point of the shifted left down. and another point which is shifted left up. I create these 2 points. I use these 2 points to generate a box called BH. And now I'm using the polygon, the ellipse polygon, and insert a hole which is made from this BH box. Okay. Now let's display what we got. And now it's an ellipse with a hole. Okay. The question is, how big is this hole in terms of width and height? You can answer that question.
What's the question?
0.4.
Yes, exactly.
Because
Okay, you can-
1.2 for one side. And
Yeah, exactly. So, and now let's check this. I will show you this is ruler. Ruler is one of the most important features in my work, because that's what I always do, like checking width and space and distance and chip size and whatever. So this is, I use 1,000 times on a daily basis. So ruler is this tool. So when I move here, you see this, the mouse cursor switches into something like a target. When I click here, this means it snaps here. Here, let me snap it to the other point, and you see it's 4. It's hard to see. Largely. Okay, let's enlarge the display a bit. Let's use X large font. That's, by the way, that's a good idea for those who are using high resolution screens. Go to Display, General, and use a default font size, which is not the standard one. Otherwise, you will see only very tiny ruler labels and in general. So you can, there's even XXX large if you like. So now it's a bit bigger, hopefully more visible. And you see it's 400, and it's also 400 in the y direction. Okay.
Excuse me, when you, so this mode, yeah, does this, is this a quick way to, instead of marking the target start and end, to just click on the edge? On the
There is. I just don't know why it's not visible here in the menu. Let me just show. Yeah, usually there are different modes for rulers, and one of them is measure. So I have to enable that again. I don't know why it got lost. There are those modes. I don't know why this wasn't a menu button. Sorry, maybe that's a bug. You see that there's some measure mode here. And in this measure mode, what it does is it will actually measure the distance. So when I click here, yeah, it will measure the distance from the closest edge to the opposite edge. So I click here, and it looks for the closest edge, yeah, then looks in the other direction, and in this case it was measuring the space between the edges and here. So it's a single click only. And I can also do the same to the outside. Is this helping you?
yes, thank you.
Yeah. Can you, by the way, can you see this measure mode on your? So no, it's not visible. Okay. This is the one from SDF, right? Okay, I don't know why. So okay, we are using actually we are using the master branch here, all of us. So if you have installed the Windows version, who has the Windows version installed? No, do you also?
I'm working on the SDF.
Who's not working on SDF? Everyone's working on
Yeah,
SDF.
no, I know.
And can I just take a look? Okay, this you have these, options. Okay, seems to be a bug in the master version. Because that's not released. In fact, it's kind of what we're doing is beta testing. Okay, I need to check what this is. Yeah.
What's the problem?
Now here, this button has a drop-down menu, and you can select multiple types of rulers. And this was not visible initially. And you can also, like, there's a ruler which just places a single cross somewhere and gives you the coordinate. Then there is one where you have an ellipse, like that. Or there's one which gives you a box, like that, right?
So the box we can see it.
The box you can see, but not the, okay.
The ruler drop down.
Yeah, you don't see the drop down menu.
Okay.
Yeah, so I assume it's kind of because that's beta. I don't know when they have pulled the version for SDF. Cannot say. It looks like being consistent with mine. Okay, Control K will delete all rulers, by the way. Control K, but you can as well configure what kind of key you have here. Okay, so, but I mean, in order to, so the question was the dimension, you see, you were right, so it's 400 by 400. I hope this kind of gives you a first impression how you can work with these objects, right? So again, here I have used a point, used center, used a vector to define the displacement, and this is eventually how you are going to work if you're coding layout. Right? You have a dimension you need to produce. By using the center, I have an exact reference to the original object. I don't need to code a specific coordinate, but I use coordinates measured from other objects. I work with points vectors to generate new objects, manipulate objects. In this case, I was inserting a hole and so on. Then what I showed, let's just do one thing. Let's save this and reopen, so you can see what I meant with this with GDS not supporting holes. This is still the canvas layout we were generating. Yeah? We have not been generating layouts by script so far. But let's just save this to XGDS, whatever.
You use holes to you use polygons with holes to make guard rings and stuff, right?
Yes, you do. I mean, let me just show you how it looks like when I saved and reopened. So just to illustrate to you, I'll open. So this is the one. So what I did is, okay, saving. I have this canvas object, canvas layout. I used file save as. Then I picked a file name, which is XGDS. That's my Scratch layout. It asks me whether to replace, and then it asks me for a couple of options. Usually, you can just use the default ones. So, unless you're interested in special behavior, just use the default options. Hit OK, and then you have generated a GDS file. And then I have reopened it, or opened it by using file open, using the same GDS. And now you see what happened is this line was generated by KLayout, this connecting line. Because now this polygon is no longer one with holes, but it's one that goes like here, around here, goes into the hole, that way around, like counterclockwise and back. And that's how such polygons are represented in GDS. And if you say you do something like a guard ring, in GDS you would have to create something that has like a connection line. If you code layout inside KLayout, the save to GDS KLayout will do this for you. It will generate this connection line for you. And you can also, the way to do this in code, you can turn a polygon with holes into a simple polygon. And the way you do it is, I hope, so I need to look this up. Okay, you I don't remember to no. I don't remember. There's no way to turn it into simple polygon. Either it's simple polygon from okay. I don't remember now. There's some way to turn it into simple polygon in scripts. I need to look it up. But the simple polygon is by definition one without holes, and then it will do this transformation for you. This inserting of this cut line. Now polygons have a lot of methods as well as boxes. Depends on what you actually want to do and what kind of polygon you have. Like here, this is the D polygon reference. Some examples. These are the constructors. You can generate one from a simple polygon, from a number of points, from a box. You can compute area. You can, what else? You can iterate the edges. So like each edge will give you all the edges of the polygon. Yeah, it will give you the number of holes. You can set the hulls or the outer contour to something. It can tell you whether it's empty or not. The polygon can be empty, so it has 0 points in fact, and so on. So like many methods here. Specific one that turns sharp corners into rounded ones. That's quite a nice feature. Sizing is a feature which generates a new polygon with shifted edges. So the edges are shifted outside or to the inside. That's a function that is often used to compensate, for example, manufacturing effects such as under etching. So you enlarge the polygon a little so that after etch, the original the polygon or the material looks like what you have drawn. That is called sizing. Sometimes it's also called biasing. That is available for polygons. You can ask whether it touches something else, whether it, and you can also ask, I think, whether points are inside. Okay, so a lot of features, in fact. So let's see whether I have forgotten something about polygons. Okay, this is just the same thing that I did. So, like inserting a hole into an ellipse. Okay, this is already paths. Well, this is the triangle I was showing you. Paths are eventually not much different from polygons. They are different, of course, but they are also built from a point sequence. So because the path consists of points that make up the center line and a width. So eventually, okay, this is bad because this is a type where it's supposed to be path and not simple polygon. So the presentation is not correct here. Let's just try what happens. So I still have no. Oops. Okay. I still have the point list from before, which gave us the triangle, and we can create a path from that. And in addition to the, let's use a smaller one. In addition to the point list, the path also needs a width. Yeah? So now let's try. That was the path I created. So I had the point list again that I used before. Unfortunately, point list is kind of, I don't know. Oh, I have overwritten it. Okay. Once again. This was the path, the point list. This is the path generated from it. And as width, I was using 0.2. And let's clear the canvas, insert. Okay, let's insert the path. Okay. So somehow I was triggering the wrong function. Okay, so now we insert the path, and it has a width of 0.1 as 0.2. Here you can roughly see it's 0.2. And the points are 0, 0, 1, 2, 2, 0, like here. Okay, so it's basically pretty simple. So point list for the center line, width for the path, and there are also additional parameters which control the end extension and the begin extension, and you can even configure it to be round-ended, which I propose not to do. But there's not much to say about paths. Paths can be turned into polygons, which will eventually create a polygon that is the outline of the path. There's one thing maybe, so this actually is good. No? Just for you to notice, this is intentional because we don't want edges to extend infinitely far. And the amount of clipping wasn't very easy to define because every tool does it in its own way. So if you send such a path to a mask maker, you cannot be sure whether the path is actually clipped at this distance, at this particular distance. It could even, for some mask makers, might extend it even further. So like when I zoom in, maybe some give you a mask that looks like that. Yeah. And imagine if that stretches into a neighboring feature. It might even connect, if that is a metal wire, that might finally connect to something else. So that's why such corners are actually not, or very, very often forbidden. If you send such a layout to a foundry, they might reject it, because that's not well defined, the behavior of this clipping. I mean, I was looking at a couple of tools, how they do it, and this was apparently the majority of tools did it exactly that way, but it doesn't necessarily mean your tool or the one using that your mask maker is using will produce exactly the same. So that's something to be very careful with. I mean, bottom line is eventually don't create acute angles with paths. And also paths can be self-intersecting, like if you make a loop and you have the path intersect itself, that's also not well defined, like for self-intersecting polygons. Okay, sorry for that typo, that should be path, not, and it should have a copy paste error. Okay, what needs to be said about paths? Not much. Okay, texts, I will just cover that briefly. Texts are funny objects, by the way. They are not meant to produce something on a mask or on the wafer, but they are usually used to mark a certain location inside your layer. And quite often they are used, for example, to attach net labels to a layer. So, for example, if you have if you generate a layout, then it's often useful to designate. I'm talking too much.
Just asking. How you doing? And
I'm doing fine.
I know, you're like in your element. However,
I don't know whether
you know what I'm scheming on the side, this like whichever template that you and Thomas, I need to have like some info. When can we set that up? So now it's 3 o'clock.
Oh, it's weird.
Yes, from 4 to 5. Maybe you will present, like update and open password. Like,
You want to stop me before 4?
I'm hoping.
No, okay.
If it's possible.
No, sure. It is. I'm sorry. That's kind of.
I know you got carried away. I would too. If I
I
had
told you
great
2
things
hours.
to present.
Okay. Yeah. Well, we will come to. I think we are closing now onto the real point where we are generating layer.
Okay. Cool.
Yeah.
I'm really sorry to be a
No. Sorry for.
Yeah. No. But I'm trying to give you today the information about what
Sure.
you kind of invited for to help us fix.
No, very good. Let's close in.
Keep going. So you know your limitations now.
Yeah, I know. Okay, thanks for letting us know. Okay, sorry. So just tell me if it takes too long. So if you think that's boring, then just make me speed up. Okay, texts, as I said, these are funny objects. So they are basically just points with a label attached to it. Yeah? They don't are not manufactured. They don't come out on the mask. But if you have, like, let's say, typically a layout which represents some gate, you want to label the points where are the inputs, where are the outputs, and then you put the text on any input shape. Yeah? So maybe there's a wire, maybe there's something else you can attach a label to, and then the layout versus schematic tool typically uses this information to assign this specific net to a certain name. And this is important because it often gives LBS tools a hint what to match against which net in the schematic, because in the schematic you use names like A, B, Q, VSS, VDD, whatever, flock, things like that. And labels are typically used to mark net names, but they can serve any purpose. So they can mark a specific position. You can put them on a polygon or you can put them somewhere else. I mean, coding-wise, texts, there are again 2 text objects. Yeah, okay, let's not touch this now. So like text and dtext, same as for polygons, and the arguments are a string, so the label you have attached, and a position, which is given in terms of what is called a transformation. I will show you this briefly, what the transformation is. I also want to mention briefly the region class, because the region class is a kind of superpower class in KLayout. A region is conceptually a collection of polygons. So you can put in 100 or 1,000 or 1,000,000 polygons into a region object. And a region supports many, many high-level features. In fact, what is in DSC tools, when you look at design rule checking tools, they often talk about layers. So the concept of such tool is to have a layer, and then you start doing measurements on this layer. And the region is actually a representation of such a layer. And the whole DSC functionality of KLayout is based on this particular object. And coding-wise, it's a container, so you generate a region object and you start feeding it polygons, boxes, whatever. And then you have a collection of polygons, and then you can start doing fancy things like checking width in space, like doing Boolean operations. Boolean operations mean computing the intersection between two areas or two polygon sets, or computing the difference or subtracting polygons from another set of polygons. And you can do clipping and all kind of manipulations. So this is a bit beyond here, what to talk about here. It can be useful to generate layout when you have layout generation rules that use, for example, Boolean operations. I'm missing that feature in Cadence, in Virtuoso. I think it's, so it used to be available in Diva, but I don't know, maybe there's a substitute for it. Anyway, this is, sometimes it's very useful because some features can be generated easily using these Boolean operations. Basically, it's a whole new world that opens when you talk about these region objects, and it's mainly about analysis and manipulation of objects in the sense of a design rule check feature. That's why I call it a superpower class. And it even supports hierarchical processing. That means if you have a design which is made for many, many subcells, and these subcells, they can be quite complex. And imagine you have 1,000 cells of the same kind. Then you can imagine that some operations are more efficient if I analyze the situation and find out I can do this locally inside the cell, but only one step. And then by doing so, I have changed the whole layout in all places. So this is quite efficient. And this region class has ways of detecting that it's a hierarchical situation. And so it can act much more efficiently than doing that on a simple set of 1,000 polygons, let's say. And it has 3 sister classes, which are edges, text, and edge pairs. And they basically form the same, but not for polygons, but for edges, texts, and something that is called an edge pair, which is basically a pair of 2 edges. But I just mentioned this here, so in case you come across that. But let's go further. We need to talk about transformations, because that's a very important concept when it comes to building hierarchies. So we are closing in on the generation of layouts. So transformations, there's some theory about transformations, which is affine transformations. I hope you have heard of that concept. So inside VLSI layout, we usually use a subset. So we are talking about transformations which shift and which rotate and maybe mirror. But we are not talking about perspective, distortion, or shear, or things like that. Sometimes we talk also about magnification, but it's a concept that is not widely accepted in VLSI layout, because whenever you scale something up, you basically change its physical properties. So it doesn't make sense to scale up a transistor, because what you get then will not be a device that behaves like your intended transistor. And also, we usually confine ourselves to rotations which are multiple of 90 degrees. So we don't use 23 degrees of rotating something. So these are the 2 components, so shift and mirror, rotation and scale. And I mean, maybe you know that, so that's the matrix way of expressing that. Usually you find, that is quite commonly used in literature, and also that one. This is just basically the same, but in a more compact form. And here you have something that is the rotation rotation matrix involving rotation, magnification, shear, whatever. And S is the shift vector. I guess you know. And then we can define a couple of operations. So these transformations form a group. I think I'm not a mathematician, so I don't think it's a group. So you have a unit element which is not transforming anything. You can concatenate, so multiply these transformations so they act, which is in our interpretation means first apply the first one and then the second one. No, first apply the second and then the first one. I can invert a transformation so it forms the opposite of the other operation, and combining both leads you to the unit transformation. Bottom line of that is a transformation. Instead of saying I shift a box, for example, or I shift a polygon, or I rotate a box in the sense of a method, I can define a transformation and apply this transformation to the box or to the polygon. And the advantage of thinking that way is that transformations are some universal concepts, and I can compute transformations. Yeah? And transformations play an important role in building hierarchies, because when I place a cell, this is basically a transformation of the content of the cell. So a cell can be placed, which means I shift everything inside a cell, but it can also involve rotations, mirroring, and so on. Right? So a cell placement is eventually the specification of a transformation. And when I build multiple hierarchies or multiple levels of hierarchies, this is just concatenating transformations. So the first level will specify one transformation, the second level will specify another one, and the resulting transformation is the product of both. So thinking in terms of transformations rather than operations means I can describe the effects of a hierarchy pretty much in terms of simple objects. And that is why KLayout offers objects that describe transformations, or a transformation as an object. And the most important ones are the ones above. So again, I have one acting on integer coordinate objects, and I have one acting on floating point objects. And one is the trans, and one is the detrans class. And these are simple transformations, just offering rotations multiples of 90 degrees. And they don't offer scaling, so no multiplication by a certain factor. They offer mirroring. So eventually leading to exactly 8 variations, but plus the shift. Yeah. So for rotations plus one mirroring option. And there's also the complex transformation, which goes beyond this. It offers all angle rotations, so like by 23 degrees, and also scaling. But as I said, this is kind of complicated in VLSI layouts. So the only thing worth mentioning here is that these complex transformations can also be used to transform between integer and floating point units and back. So that's how they are mainly used in KLayout in VLSI. And these transformations can be applied to objects. So if I define such a transformation, I can multiply an object with it, and I get the resulting object. Right? And I can briefly demonstrate this to you. So let's see what we have this part here, for example, that we were just experimenting with, this one. And let's figure out what happens if I use a transformation. So first of all, I need to create a transformation. We need a detrans object because we act on floating point types, because I have a B part here. Let's just create that. Okay, imagine this blank is after the comma. This one creates a transformation which is a shift only. so a displacement by 2 in x direction and 3 in y direction. And let's apply this to, let's insert the thing that I get when I multiply this t with the path. And then you see okay. Stupid. Okay, I created already a different transformation. Let's do the full thing. Okay, that's a stupid pitfall. Let's do that again. I'll explain you why this happened. Okay, so this will give me a shifted path. It's that one. And here it's shifted by 2 in x direction and 3 in y direction. Yeah? And what I did initially, this one, the first one, is actually a variant which is specifying a rotation and a mirroring. So a rotation is given by a multiple, so by the angle in multiples of 30 degrees. So that would be 180 degrees. Then I can specify whether mirroring is involved or not. And then I can, in addition, specify a shift. So that's the full version of transformation. So this is 180 degrees. This means no mirroring, and this means no shift. Yeah? I can also specify that as a vector. Vector. So, and so this means I need to insert it. So here I now get I have this one and I have the rotated version 180 degrees. Okay, let's take a look at. So this is the transformation. R 180 means rotate by 180 degrees. Right? So now that's so far easy. The mirroring comes into play in a specific way because it means before I apply the rotation, mirror at the x-axis. So first flip up down. If I specify mirroring, like here, if I use true instead of false, I specify mirroring to be involved, and what I get then is like that, this one. So because first thing I do is I flip the whole thing down, right? And then I rotate by 180 degrees. So, and the same thing is equivalent to mirroring at the 90-degree axis here, as you see. And that's why this kind of transformation prints as M90. M90 means mirror at the 90-degree axis, which is the y-axis. And eventually I have four kinds of transformations available here, which is mirror at 0, so at the x-axis, mirror at 45 degrees, so then it's flipped at the diagonal, at 90 degrees and at 135 degrees. And these are the 4 variants that KLayout offers as simple transformations. And this should be here. So this is a pretty important slide. But this is also in multiple places in the documentation. So these are the 8 variants that are offered for simple transformations, plus the displacement, of course. Shift is always included. And this is sufficient to describe all cases of rotation by 90 degrees plus some kind of mirror. So this F is typically used to indicate what comes out, because F is not symmetric, so you can always tell where the original was and how it was transformed. And here, so these are the codes for the transformations, and you can memorize that by by knowing that the angle that is mentioned here, so like N45 means mirror at the 45-degree axis, 45 in the mathematical sense. So this here is the result when you take this F and flip it at this axis. And the other, the four without mirroring involved, these are the left side ones. That's simple. So we always talk about mathematical rotation, so counterclockwise. So F is rotated. This is the 90-degree, like this, rotated by 90-degree counterclockwise, 180, 170. Wow. It's only 8 versions, so well, this is called fixed point transformations because without the displacement, there's always one point that stays fixed, which is 0, 0, 0 location to origin. Okay, I mean, so that is what we are talking about when we talk about simple transformations. The complex transformations, as I said, they are usually not used. This is basically how you can use them to convert database units or integer unit types into database unit types. Well, I don't know whether it's useful as of now. What it basically does, it generates such a complex transformation, giving the database unit as a magnification factor, and then inverting that, because multiplying by the database unit converts integer to floating point. If you invert it, you convert floating point to integers. And if you apply that to a floating point object in micrometer units like that, then you get an integer unit object. And inverted is the method which returns the inverted transformation.
So if you want to create a region out of polygons, you have to do this first before you create the region.
Yeah, do you know? Do you ask because you know it, or because
I'm confirming if.
Yeah, you have to. Yeah, that's true. I didn't explicitly mention this before, but it was written on the slides. This region object is only for integer type polygons. Yeah. So.
Yeah, I was thinking because it might be that,
I
like,
just
when
wanted
you
to ask whether you
region.
have some experience already with this. No, you don't. Okay. That's actually a good question. Yeah, you're right. So I'm right now. I'm only using these floating point unit objects. If you want to work with this region class, then you have to turn it into integer unit ones. Okay, but it's like that's. I would say that's an advanced topic how to work with that class. And I think it's when it comes to, let's say, generating layout as in the sense of not having to draw it, you don't need this region object as of now. But you're right, so thanks for asking, basically. But that's eventually a way of doing that. And I have written code myself. I use this a lot in order to enter integer unit space. That is one point. That is one important thing here to know. Transformations apply to points and vectors, but for vectors, they do not include the shift. And the rationale of this is this formula. If you take the difference of 2 points, which is the definition of a vector, and you apply a shift to both points, the shifts will cancel. So a vector, when you apply a transformation to the difference of 2 points, the result will not depend on the shift vector. So that is why vectors are transformed differently than points. But that's like part of the hierarchical framework. Okay, so now let's welcome to the climax. So this is where we are here. because we finally want to generate layout, right? We don't want to generate polygons, we want to generate layout, things we can save to GDS, okay? And just in order to give you some tool to try this out, what I'm going to show, I have prepared a second gist. Let's go there. I will paste now, come on. Okay, I don't want to. Okay, then let's paste it from here. Where's this? So then please create a new macro called display and paste the code that is inside this gist. It's pretty short, in fact. So what it does, there's not much magic here. It just takes a layout, I will give it, and puts it into a tab in the application. So we can look at the layout rather than just having a layout object, right? A layout object is always a bit, it's too abstract. And there's no print function for a layout. That's why it's difficult to see what's happening. Did you receive this link for this gist? Okay. So it should look like that. Should I paste it again? No, it's okay. I mean, if you're interested how this works, it's eventually very simple. So here it accesses the main window instance, so which is also an object, so the main application window. And here it generates a new tab. It opens a new tab and then shows the layout inside this tab. And it does one thing which is important. It creates a copy of this layout. So .pop creates a copy of the object. And the reason why I do so is when I show a layout in the tab and you start playing with it, and at the same time I start manipulating it in a script, it's quite likely that the application crashes. That is because the Python objects eventually point directly into the memory of the application. And that is usually, well, kind of tricky because when you start changing this layout, for example, you select a thing, you delete it, you basically change the Python object and vice versa. So, and each of the parts doesn't know what the other does. So as an application that is written in C++ usually assumes there's no Python tweaking with its internals and the other way around. And so if I don't generate a copy here, it's quite likely that you manage to crash the application when you play with this layout we are just showing. So, and this already indicates that, let's say, the whole thing is not super stable, right? So if you generate layout by scripting, it's okay to generate a layout, save it to a file, maybe even showing it. But if you like expect interaction between both, that's probably, I mean, it's very easy to crash the application if you don't care, if you don't look carefully. So don't be disappointed when you do some experiments yourself, you try certain things, copy paste code from here and things like that, and you find the application crashing. It's almost in all cases not your fault, but it's like the application making assumptions that no one else is tweaking with its internals. I mean, the architecture-wise, this is because it's very easy to work with pointers and very efficiently. And then it's very efficient to work with pointers inside the C++ application. But pointers tend to become invalid, so they point to memory locations which are no longer valid. And if this happens, you get segmentation faults or all kind of crashes. So to make the application efficient, you cannot store all this. You can mitigate this problem by keeping management information inside your code, which does like reference counting, for example, and things like that, but it all takes memory. And it's a trade-off between spending memory and also CPU cycles on such management or not. And in this case, KLayout is more like on the vulnerable side, I'd say. So I'm trying to kind of eliminate the worst scenarios so that they work. Most of that works somehow, but it's still quite easy to crash things. But here, this duplication generates a copy, and then you pass it an object, the object is copied, and then you can do whatever you want with this object, and there's no risk of crashing or anything. So, yeah. That is all not a problem if you work with the Python module, for example. So because the Python module, there's no user interface, which depends on integrity of some data structures. So in this case, you don't need to worry. Okay. Well, having said this, I think we can move to where's that?
Matthias, can you maybe finish quarter 2 4 such that participants can go to the toilet, grab a coffee before the next talk? What do you think?
Yeah, I'm almost done.
Sorry. Thanks.
It's my fault. Okay, let's go to the final step. Come on, I don't want to open this. Where's my? Did I close? Ah, sorry. I want to do this one. Okay, so a few words about layouts in general. So layout is the overall thing, right? The thing that you put into GDS, the thing that we have been editing before. A layout is made from cells form a hierarchy, and it's made from layers. And the objects inside KLayout representing this is the layout object itself. It's a cell object, so representing a single cell. And it's the layers, and the layers are represented as shapes. Shapes is a class, which is each cell has a set of shapes, and the shapes correspond to the layers you have defined in the layer. This is the basic structure. And in order to generate a layout, here's a few simple steps. So let's do this quickly. First thing is going to create a layout. Second thing is it needs a database unit. I can skip this step because this is the default database unit. Then let's generate a layer. Okay. Hey, you're quick in typing. You don't need to follow all of that. Let me just show that in order to save some time. Then next thing is I will create a top cell. So this is the initial cell I need. Then I'm going to access the shapes collection of this top cell and for this given layer. So a layer, by the way, is represented by some ID, which is an integer number. And then I can start putting in shapes. So like the famous box. What happened? Okay, it works. Okay, very good. So then we put in the box into the shapes. And then let's display that. Okay, I have not run this. So you need to run this gist first. So now we should see a tab with the box. Okay, and this is already a complete layout. I mean, it's a simple one, but it's a complete. So, and what we did now, we were talking a lot about these geometrical primitives, boxes, polygons, text, whatever, how to manipulate them. But this is how you publish them. Yeah? This is how you assign them to a layer. So first step is we define the layers inside the layout. We get some IDs back, which are integers. Then I define cells, and then I attach these geometrical primitives to shapes inside layers, inside cells, to layers inside cells. And that's how I assign layers to polygons. Okay. Yeah, and then I can basically go ahead and write this to a file. So let's write this to XGDS. So somewhere, I don't know now where I am. You can usually would write that to some path, but now I have generated a GDS file. So this is eventually how you produce layout. Of course, not usually it would be not that easy. It would be more difficult with a lot more lines. But now this is putting together all the things. It's important to know that we have this shapes class. So cells have a number of shape containers, and in order to fill geometric primitive into a cell, into a specific layer, we need to get this shapes object by asking the cell to return it. So like here, this is the important thing. ID is what the integer we got for the layer we are looking for, and the shapes object or container is the thing we fill the shapes into. Yeah. And once they are inside the cell, they are basically stored inside the database. This is how I stash these these primitives into the geometry database. And it's not that easy to get them out again. You can do so, but then you're dealing with different objects, no longer with box, polygon, and so on. But then you're dealing with a shape object, which is then either box, either polygon, either a text. And once you have stashed these objects into the database, they are no longer a floating point unit, they are integer unit. And then they are referring to a database unit. And the last thing which is important is basically only knowing, this is writing. Okay, congratulations. And I will just go through that briefly. In order to generate an instance, in order to place a cell, there are two objects which represent a cell instance. So a cell instance is basically a transformation and a cell name. But the cell name is not, or in KLayout you don't use cell names, but you use something that is called a cell index, which is a kind of number representing a certain cell. So what we did here, we created a top cell here. So what we got back is a cell object, and the cell object has something that is called a cell index, and this is 1. Because basically it's the first cell. Okay, it could be 0. Anyway, so it has an index. And using that index and using a transformation, I generate instance. And I do so by creating an object which is of type D cell inst array here. So this is just a wrapper for these both types of information. It's always called cell inst array. There is no cell inst without array because it can also represent these arrays I've shown you before, these big array things. I give it the cell index, I give it a transformation, which means I want to place the cell here or rotate it, depending on what I put into this transformation. And then I simply insert this object into a cell. And after I have done so, I have created an instance. And this instance means then this original cell is placed there. And I can also use the same object to create an array. Well, I don't know. Oh, okay. We have 1 minute. I mean, eventually, these are probably things you need to play with, right, to get some feeling about that. Here's some code. You will find that in the presentation. You can execute this code. It will generate a unit cell. It will generate a top cell. It will place the unit cell once, which is this lower thing here. So that one, and it will also generate an array. And in this case, I specified to rotate it by 45 degrees, which is, as I said, something you shouldn't do usually. But in this, it also shows that rotation comes before array formation. So the cell is rotated, and then I form the array. And the array is specified by two vectors, like one axis, the second axis, and then the number of steps in both directions. And that's it. And then you save the thing, and then you have a layout.